For centuries, humanity has sought to understand the cosmos, gazing at distant stars and probing the smallest particles. We believed we were searching for the fundamental building blocks of reality, matter, energy, the very stuff of the universe. But what if that belief is fundamentally flawed? What if the universe is not built from tangible bricks, but from something far more ephemeral, yet infinitely more profound? Information itself. This radical idea challenges the very foundation of what we consider real, forcing us to question everything we thought we knew about existence. It was the American theoretical physicist John Archibald Wheeler, in the late 20th century, who famously encapsulated this unsettling hypothesis with the phrase "it from bit." He proposed that every physical object, every fundamental force, even space-time itself, does not originate from solid particles or invisible waves, but from binary yes or no answers to questions posed at the quantum level. To put it another way, the universe, in this view, functions less like a sprawling cosmic machine and more like an unimaginably vast, intricate computer program, where every observable phenomenon is a product of underlying informational code. This perspective suggests that the universe is not fundamentally made of matter and energy in the way we traditionally conceive them, but rather that these are emergent properties arising from information. Consider the digital world we inhabit today. Every image, every sound, every complex calculation on our screens is ultimately composed of billions of simple bits, zeros and ones. Wheeler's concept hints at a similar, yet infinitely more complex, underlying digital architecture for the entire cosmos, where reality is constantly being computed through fundamental informational exchanges. One of the cornerstones of this informational universe theory is the Bekenstein bound, a concept developed by Israeli physicist Jacob Bekenstein in 1972. This groundbreaking idea suggests that any given region of space has a finite limit to the amount of information it can contain. Think of it like a cosmic hard drive with a maximum storage capacity. No matter how large an area or how much energy it holds, there is a quantifiable maximum number of bits that can describe its state. This constraint directly links information to the physical property of entropy, which we often associate with disorder, but can also be understood as a measure of the total information contained within a system. This direct connection between information and fundamental physics was further revolutionized by the holographic principle, championed by Dutch Nobel laureate Gerard Hooft in 1993 and later expanded upon by American physicist Leonard Susskind. They proposed an idea so mind-bending it could rewrite our cosmic address. The entire three-dimensional universe, with all its galaxies, stars, and living beings, might in fact be a projection. Our seemingly solid, three-dimensional reality could be a cosmic hologram encoded on a distant, two-dimensional surface, much like a security hologram on a credit card contains a three-dimensional image on a flat plane. If our reality is indeed a hologram, the implications are profound. It means everything we perceive, every star we observe, every atom we detect, could be an intricate display of data points from a far-off, less dimensionally complex boundary. This isn't science fiction. It is a serious proposition within theoretical physics, attempting to reconcile some of the deepest paradoxes of our universe. The question becomes less about what the universe is made of, and more about how it is encoded. Look to the strange world of quantum mechanics, where phenomena like quantum entanglement seem to make more sense through this informational lens. When two particles become entangled, their fates are linked, no matter the distance separating them. A measurement on one instantaneously affects the other, a connection Albert Einstein famously called spooky action at a distance. But if reality is fundamentally information, then perhaps these particles are not truly separate entities traversing vast distances, but rather different manifestations of the same underlying information bit, already connected within the cosmic code. Even the enigmatic nature of black holes lends credence to this informational view. Black hole thermodynamics, particularly the discovery that black holes slowly evaporate through what is known as Hawking radiation, presented a profound challenge to physics. If matter falls into a black hole and the hole eventually evaporates, what happens to the information contained within that matter? The idea that information could be permanently destroyed fundamentally clashes with the core tenets of quantum mechanics. This conflict, known as the information paradox, has pushed physicists to explore theories where information is preserved, subtly encoded on the event horizon of the black hole, further cementing information's fundamental role in the universe. This perspective forces us to fundamentally reconsider what existence truly means. The universe shifts from a collection of stuff to an intricate, dynamic script. It is a move away from tangible components and towards the underlying programming that governs their behavior. Instead of searching for the ultimate particle, we may be on a quest to decipher the ultimate code, the cosmic language that gives rise to everything we experience. This shift also redefines our own place in the cosmos. If reality is a cosmic script, then how do we, as conscious observers, interact with it? Are we merely readers of this script, or do our observations, our very questions, play a role in its unfolding? This informational view sets the stage for a deeper understanding of our connection to the universe, suggesting that our consciousness may not just be a byproduct of reality, but an integral part of its ongoing computation. If the universe truly functions as an intricate, evolving script, then who exactly is reading it? And more critically, who is writing it? For centuries, we believed we were merely passive observers, meticulously decoding an objective reality. But what if our very act of observation, our interpretation, is not a detached scientific endeavor, but a process as ancient as humanity itself, fundamentally shaping the cosmic story rather than just discovering it? Before we can even begin to understand the cosmos as some grand, objective entity, we must first confront a more uncomfortable truth: how we tell stories about it. This journey does not involve the familiar narrative of telescopes and mathematical breakthroughs, from Ptolemy's geocentric models to Copernicus's revolutionary heliocentrism. Instead, we must travel back through time, delving into the deep psychological and social construction of the universe, recognizing that our perception has always been a profoundly human act. Consider for a moment the Nebra sky disk, a remarkable bronze artifact unearthed in Germany. Dated to approximately 1600 BCE, it is far more than a mere primitive astronomical chart. This object, roughly the size of a large pizza and weighing around 4.5 pounds or 2 kilograms, is a profound synthesis of celestial observation, religious mythology, and political authority. It displays the moon, the Sun, and the Pleiades star cluster, a grouping of stars easily visible to the naked eye. But its purpose extended beyond tracking the seasons. It was a cosmic calendar, a sacred object, and a tool of power, allowing the ruling elite to claim divine insight and control over agricultural cycles by predicting celestial events. The patterns etched onto this ancient disk were not just reflections of the sky, but of human order, human belief, and human power structures. Our journey continues further back, to the colossal Neolithic passage tomb of Newgrange in Ireland. This monumental structure, built around 3200 BCE, predates the Great Pyramid of Giza by 500 years. It is a massive undertaking, comprising over 200,000 tons of stone and earth, covering an area larger than a modern football field. Every year, at the winter solstice, the rising sun precisely aligns with a narrow opening above the entrance, illuminating the central chamber with a shaft of light that travels over 60 feet into the heart of the tomb. While this incredible precision speaks to an advanced understanding of celestial mechanics, it was not merely a feat of pure science. This alignment was a deliberate act of social engineering, designed to reinforce community bonds during the darkest days of the year, to regulate vital agricultural cycles, and to powerfully demonstrate the authority and cosmic connection of the ruling elite. The cosmos was not just observed, it was utilized, woven into the very fabric of society to maintain order and hierarchy. Through the fascinating discipline of ethnoastronomy, pioneered by brilliant figures like the American scholar Anthony Aveni, we gain an unparalleled insight into this intricate human-celestial relationship. Aveni and his colleagues have shown how diverse cultures spanning continents and millennia, from the sophisticated astronomers of the ancient Maya civilization in Mesoamerica to the rich, millennia-old traditions of the Aboriginal Australians, projected their earthly concerns, their complex social structures, and their deepest anxieties onto the vast celestial canvas. The constellations they identified, the myths they wove around the stars, were not arbitrary. They were reflections of their hunting practices, their kinship systems, their moral codes, and their fears of the unknown. A star cluster might represent a hunting party, a line of planets a journey, or a meteor shower a sign of divine anger or blessing. This exploration into the ancient past reveals a crucial, unsettling truth about our relationship with the cosmos. Our perception of the universe has never been a purely objective act of discovery. It has always been, fundamentally, a creative act of interpretation. The patterns we identify in the endless expanse of the night sky are not always inherent features of the cosmos itself. More often, they are powerful reflections of the patterns hardwired within our own minds, shaped by our societies, our cultures, and our innate human need for narrative and meaning. We are not just looking at the universe. In a profound and inescapable way, we are always looking through ourselves, making us inherently unreliable narrators in the grand cosmic story. Our ancestors gazed at the night sky, weaving narratives of gods and destiny into the celestial tapestry. They projected their deepest fears and grandest aspirations onto the cosmos, shaping the universe in their own image. But what if that projection, that act of observation, is not merely a human bias, a flaw in our cosmic storytelling, but a fundamental interaction with reality itself? What if the universe is not a grand, indifferent stage upon which we merely act, but a dynamic entity that actively responds to our very gaze? This unsettling possibility transports us from the vast, familiar expanse of galaxies and nebulae into the bizarre, counterintuitive realm of quantum mechanics. Here, at the smallest scales imaginable, the observer is no longer a passive spectator, peering through a telescope from a safe distance. Instead, the act of looking, the very process of measurement, transforms into an active participation, seemingly molding reality from a cloud of probabilities into something concrete and undeniable. This is where the universe, in a sense, truly reveals its ghostly nature. The cornerstone of this quantum mystery is an experiment so elegant, yet so profoundly disturbing, it has baffled physicists for nearly a century, the famous double-slit experiment. Picture a stream of tiny particles, like electrons, fired one by one towards a screen containing two narrow slits. Behind this screen, a detector waits to record where each particle lands. If these were ordinary particles, we would expect to see two distinct bands on the detector, corresponding to the electrons passing through either the left or the right slit, much like bullets shot through two holes in a wall. Yet, when this experiment is performed, the outcome is astonishingly different. Instead of two bands, the electrons create an interference pattern, a series of alternating bright and dark fringes, precisely what one would expect if they were waves, not individual particles. It is as if each electron passes through both slits simultaneously, interfering with itself before recombining. The truly mind-bending twist comes when scientists attempt to observe which slit each electron actually passes through. The moment a detector is placed at the slits, the interference pattern vanishes. The electrons suddenly behave like ordinary particles, forming two distinct bands once more. The act of observation, of simply looking at the electron's path, forces it to choose a single reality, collapsing its wave-like probability into a definite particle. This is not merely a demonstration of wave-particle duality. It is a profound philosophical riddle about the nature of reality itself before it is measured, suggesting that particles exist in a fuzzy state of potentiality until conscious observation brings them into being. This radical notion led the brilliant American theoretical physicist John Archibald Wheeler, a towering figure in 20th-century physics, to propose his audacious participatory anthropic principle. It is a speculative idea, yet one that echoes through the deepest chambers of cosmological thought. Wheeler suggested that the universe, through some unknown and deeply mysterious mechanism, achieves a concrete, definite state of existence only when observed by conscious beings. The very laws of physics, the stars, the galaxies, might exist in a kind of quantum superposition, a state of unformed potential, until minds like ours emerge within it to ask questions and take measurements, thereby writing the universe into being. Consider the mind-bending implications of the delayed choice quantum eraser experiment, a real-world scientific endeavor that pushes these boundaries even further. In a compelling form, this experiment was first realized by a team led by the physicist Yoon-ho Kim in South Korea in 1999. It involves a sophisticated setup where the choice of whether to reveal the path of a photon, and thus erase its wave-like interference pattern, is delayed until after the photon has already passed through the double-slit apparatus and hit the detector. Astonishingly, The results seem to indicate that a measurement made in the present, a choice made by an observer now, can retroactively influence an event that has already happened in the past. It is as if the universe is not just waiting for us to observe it, but is actively rewriting its own history based on our present-day decisions, blurring the lines of cause and effect in ways that challenge our most fundamental intuitions about time. These quantum paradoxes gave rise to vastly different interpretations of reality. One of the most prominent is the observer-centric Copenhagen interpretation, developed by the visionary physicists Niels Bohr and Werner Heisenberg in the 1920s. This view asserts that quantum particles do not possess definite properties until they are measured. The act of observation causes the wave function of a particle to collapse, forcing it into a specific state. In this framework, the observer is intrinsically woven into the fabric of reality, a necessary catalyst for its actualization. Without an observer, the universe, at its most fundamental level, remains a realm of mere probabilities. However, not all physicists subscribe to such a privileged position for the observer. Hugh Everett III, an American physicist, proposed the radical many-worlds interpretation. This alternative view attempts to remove the observer from their seemingly central role. Instead of a wave function collapsing into one definite state upon measurement, Everett suggested that every possible outcome of a quantum measurement is realized, but in separate, parallel universes. When an electron passes through the double slits, it does not choose one path. Rather, the universe splits, with one version of reality seeing the electron go through the left slit and another seeing it go through the right. In this view, reality is constantly branching, an infinite cosmic tree, and we, as observers, simply follow one particular branch, unaware of the countless others. The central, profound question that emerges from this quantum labyrinth is whether the reality we study, the cosmos we explore with our telescopes and particle accelerators, is a pre-existing, independent entity, fully formed and awaiting our discovery. Or, in a far more unsettling and exhilarating possibility, is the very act of looking, of asking questions, of devising experiments, in some fundamental way, helping to write the story we are trying so desperately to read. Are we merely deciphering a cosmic manuscript, or are we, with every observation, adding our own indelible verse to its ongoing, evolving narrative? Beyond the quantum observer and the stories we weave, the cosmos holds its ultimate secrets with a fierce, uncompromising grip. Its most profound truths are not merely hidden, but actively guarded by forces so extreme they redefine the very limits of what we can know. The universe is not an open book. Instead, it contains locked rooms and redacted pages, and its ultimate guardians are the most enigmatic entities known to science: black holes. These cosmic behemoths are not just devourers of matter, but also the universe's appointed censors, standing at the very boundaries of our understanding. For decades, physicists grappled with the implications of regions in spacetime where gravity becomes so intense that nothing, not even light, can escape. At the heart of a black hole lies a singularity, a point of infinite density and curvature where our current theories of physics simply break down, much like a mathematical equation attempting to divide by zero. It is a place beyond comprehension, a theoretical abyss. But what prevents us from observing these naked singularities, these regions where the laws we rely upon dissolve completely. It was the British mathematical physicist Roger Penrose, in 1969, who proposed his audacious cosmic censorship hypothesis. This idea posits that the universe itself has a fundamental safeguard in place. The laws of physics, Penrose suggested, conspire to hide all singularities behind an impenetrable veil, the event horizon. This is not just a point of no return for matter and energy, but something far more profound. It acts as an epistemological boundary, a fundamental limit on what we can ever observe or know about the universe's most extreme states. Consider it a cosmic curtain, drawn forever, ensuring that the bizarre physics of the singularity never directly impacts our observable reality. Any object, whether a star 20 times the mass of our Sun or a single photon of light, that crosses this threshold is forever lost to our view, its information seemingly vanished behind this one-way membrane. Yet, just 5 years later, another brilliant mind would ignite a paradox that shook the foundations of both relativity and quantum mechanics. In 1974, the legendary British theoretical physicist Stephen Hawking made a discovery that seemed to contradict everything we thought we knew about black holes. They evaporate. Through a process now known as Hawking radiation, black holes slowly leak energy back into space, eventually fading away over an incredibly vast span of time. For a black hole with the mass of our Sun, this process would take longer than the current age of the universe, a staggering 10 to the power of 67 years, or a 1 followed by 67 zeros. Hawking's calculations suggested that as a black hole radiates away, it would carry no information about what fell into it, other than its mass, charge, and angular momentum. This meant that the quantum information of every particle, every atom, every book, every memory that ever crossed the event horizon would be permanently destroyed. This concept flew directly in the face of one of the most basic tenets of quantum mechanics, the principle of information conservation. Quantum mechanics dictates that information can never be truly lost, only transformed or redistributed. It is as if you burned a book, and every single letter, every concept, every single bit of data simply vanished from existence, leaving no trace. This conflict became known as the information paradox, a profound theoretical battleground that pitted two of physics' most successful theories against each other. The battle raged for decades, a war of ideas waged in the minds of the greatest scientific thinkers. It forced physicists to confront the deepest nature of reality, questioning whether the universe was fundamentally deterministic or if true information loss was possible. Could the cosmos truly erase its own memory? Many solutions were proposed, some involving parallel universes, others suggesting that information somehow escaped in a scrambled form. It wasn't until 2016 that Stephen Hawking, alongside his collaborators Malcolm Perry and Andrew Strominger, proposed a modern, speculative solution known as soft hair. This revolutionary idea suggests that the event horizon of a black hole is not as smooth and featureless as previously thought. Instead, it might possess a subtle quantum imprint, a kind of soft hair that encodes the information of everything that falls in. These soft hairs are thought to be massless, zero-energy particles, a ghostly memory of the matter that has crossed the threshold. This proposal hints that information isn't destroyed, but subtly encoded on the two-dimensional surface of the event horizon, much like the holographic principle suggests our entire universe is encoded on a distant surface. It means that the seemingly impenetrable boundary of a black hole might in fact be a cosmic hard drive, continuously updating its record of everything it consumes. This journey to the edge of space and time reveals that the universe doesn't just challenge us with its vastness, a scale so immense that a single galaxy can contain billions of stars, each one 1,000,000 times larger than Earth. It also confronts us with its fundamental unknowability, forcing us to grapple with the profound possibility that some questions, some ultimate truths about reality, may be permanently beyond our grasp, hidden behind the cosmic curtain. The universe confronts us with its limits, with vast stretches of unknowable space and fundamental boundaries of knowledge. Yet, within this very frontier of understanding emerges the most relentless force we know, life itself. Why do we, as conscious beings, tirelessly strive to map galaxies, decipher quantum mechanics, and seek out cosmic truths? Is this grand scientific and philosophical quest merely a cultural pastime, a complex hobby for an advanced species? Or is it, in fact, a continuation of a profound, fundamental biological imperative, a drive as essential as breathing or eating? This radical idea proposes a sweeping synthesis of biology, thermodynamics, and cosmology. It suggests that our insatiable hunger for knowledge is not an accidental byproduct of intelligence, but an inherent strategy for survival, woven into the very fabric of living systems. To trace this astonishing connection, we must first look to the insights of the Austrian physicist Erwin Schrödinger, who in his seminal 1944 book, What is Life, offered a revolutionary perspective on living organisms. He described life as a unique phenomenon, a system that maintains its intricate internal order not by defying the universe's inexorable slide into disorder, known as entropy, but by actively feeding on order from its environment. Consider a delicate, vibrant flower, meticulously structured with petals and stamens. Over time, all systems naturally tend towards a state of greater disorder, just as a perfectly built sandcastle will inevitably crumble under the relentless assault of waves. But the flower, unlike the sandcastle, actively resists this decay. It draws energy from sunlight, nutrients from the soil, and carbon dioxide from the air, all highly ordered forms of energy and matter. It then uses this collected order to maintain its own complex structure, to grow, and to reproduce, effectively creating pockets of increasing local order in a universe that is otherwise gradually unwinding towards maximum chaos. This constant battle against entropy, this relentless pursuit of order, is the hallmark of all life. Connecting this foundational biological struggle to the cutting edge of neuroscience brings us to the groundbreaking work of British neuroscientist Carl Friston and his powerful free energy principle. This ambitious theory, often hailed as a grand unifying theory of the brain, posits that all living systems, from the simplest single-celled bacterium to the most complex human societies, are fundamentally prediction machines. Their primary goal, according to Friston, is to minimize surprise or free energy by constantly building better and more accurate models of their surroundings. An organism in a state of high free energy is surprised by its environment. it encounters something unexpected, something that does not fit its internal model of how the world works. To reduce this surprise, the organism must either update its internal model to better predict the world or actively change its environment to better match its existing model. Imagine a bacterium navigating a chemical gradient in its watery environment. It builds an internal, albeit simple, model of where nutrients are abundant and where toxins lurk. When it encounters an unexpected concentration of a chemical, it experiences a surprise. To minimize this surprise, it adjusts its movement, refines its internal chemical map, and continues its relentless quest to predict and control its immediate surroundings. In a strikingly similar fashion, an astronomer, gazing through a telescope, meticulously charting the motions of distant galaxies and piecing together the story of the early universe, is engaged in the exact same fundamental activity. They are building an increasingly complex and accurate model of their environment, the cosmos itself, to minimize the surprise of unexplained phenomena, to predict the future behavior of stars, or to reconstruct the universe's distant past. From this astonishing perspective, the most sophisticated expressions of human endeavor, science, philosophy, and art, are not abstract intellectual pursuits detached from our biological roots. Instead, they represent the apex of this deep, inherent biological drive. The quest to understand the universe, to create theories that encompass everything from the smallest subatomic particles to the largest cosmic structures, is nothing less than an attempt by one part of the universe, us, to create a complete working model of the whole. It is the ultimate act of minimizing uncertainty, a cosmic dance of prediction and refinement, where every discovery, every new insight, brings us closer to a state of perfect, seamless understanding. We have journeyed through cosmic scripts and biological imperatives, daring to suggest that our very quest for knowledge is woven into the fabric of life itself. But now, it is time to turn that critical lens inward, to dissect the primary instrument of our understanding, the human brain. For all its astonishing capacity to unravel the universe's deepest secrets, this 3-pound organ, shaped over millions of years on the ancient African savanna, harbors a profound and systematic bias that fundamentally distorts our perception of the vast, impersonal cosmos. This is not a story of distant stars misleading us, but of our own minds creating patterns where none truly exist. Consider the human mind's innate drive to find meaning, to connect disparate dots into a coherent narrative. This profound cognitive tendency has a name: apophenia. It is the spontaneous perception of meaningful connections or patterns in random or meaningless data. Its even more specific cousin is pareidolia, where we see familiar shapes, often faces, in ambiguous stimuli. Think of staring at a cloud and seeing the profile of an ancient king, or spotting the vague outline of a smiling face on the surface of Mars. These are not mere whimsical observations. They are deeply ingrained neurological phenomena, a testament to our brain's relentless pattern-seeking nature, honed by an evolutionary past where identifying a predator in rustling leaves or a food source in scattered tracks was the difference between life and death. No historical figure better encapsulates this cosmic bias than the American astronomer Percival Lowell. In the late 19th century, fueled by earlier, vague observations from Italian astronomer Giovanni Schiaparelli, Lowell dedicated his life and fortune to studying Mars. From his private observatory in Flagstaff, Arizona, equipped with powerful telescopes that were among the best in the world, he spent years meticulously mapping what he firmly believed was an intricate network of canals crisscrossing the Martian surface. His detailed drawings showed hundreds, then thousands, of linear features, some stretching for hundreds of miles, connecting what he interpreted as oases and polar caps. Lowell was convinced these were not natural formations, but the monumental engineering works of an advanced, dying Martian civilization, desperately trying to channel water from the poles to their arid equatorial cities. The public was captivated by Lowell's vision of a dying Martian race, which profoundly influenced popular culture and science fiction for decades. Yet, as telescopic technology advanced, revealing clearer images of Mars, the grand network of canals slowly, then decisively, evaporated. They were revealed to be a complex combination of optical illusions within the limits of existing telescopes, the human eye's tendency to connect faint, disjointed features, and indeed, wishful thinking driven by a passionate desire to find life beyond Earth. Lowell's meticulous maps, so precise in their detail, were not a record of Martian geology, but a projection of his own pattern-obsessed mind onto the distant red planet. His story serves as a stark reminder that even the most dedicated scientific observation can be fundamentally skewed by our brain's inherent biases. To understand the neurological roots of this profound tendency, we can turn to the groundbreaking work of contemporary neuroscientists like Michael Gazzaniga. His pioneering research with split-brain patients, individuals who had the corpus callosum, the bundle of nerve fibers connecting the two hemispheres of the brain, surgically severed, revealed a fascinating cognitive module. Gazzaniga termed this remarkable function the left brain interpreter. He discovered that the left hemisphere of the brain, largely responsible for language and logical reasoning, constantly strives to create coherent narratives and explanations for everything we experience, even when the information it receives is incomplete, contradictory, or entirely random. Imagine a split-brain patient shown an image only to their right hemisphere, which controls the left side of the body. If instructed to pick up an object related to that image with their left hand, they would do so correctly, but when asked why they picked it up, their left brain interpreter, having not seen the image directly, would invent a plausible yet entirely false explanation. This interpreter is a tireless storyteller, always seeking to impose order, causality, and intention on the world, whether or not such connections genuinely exist. This deep-seated need to create causal narratives and assign agency is precisely what makes us profoundly susceptible to seeing intention in the cosmos itself. This cognitive architecture explains why humanity is so drawn to concepts like the fine-tuning of physical constants, the idea that fundamental cosmic parameters, from the strength of gravity to the mass of an electron, appear perfectly calibrated for the emergence of life. While this is a legitimate area of scientific inquiry, our brains are wired to interpret such coincidences as evidence of deliberate design or cosmic intent, rather than simply as a brute fact of existence or the outcome of a vast multiverse. Similarly, when we listen to ambiguous signals from deep space, our innate interpreter eagerly searches for patterns, for messages, for the echo of another intelligence, even in what might simply be cosmic background noise. This ancient brain, evolved for survival in a complex but relatively small world, struggles to grapple with the truly vast, impersonal, and often random nature of the universe. This chapter, therefore, serves as a crucial and humbling check on our intellectual hubris. It forces us to question how much of the cosmic order we believe we discover is a genuine, objective feature of the universe, and how much is merely a magnificent, yet ultimately self-imposed, projection of our own pattern-obsessed minds. The universe is out there, indifferent and immense, but our perception of it is filtered, interpreted, and sometimes entirely fabricated by the very tool we use to see. We have charted the cosmic narratives woven by our ancestors, deciphered the unsettling ghost in the quantum machine, and confronted the universe's own profound limits on knowledge. Yet, after exploring how our own minds might bias our perception of the cosmos, a far more chilling question inevitably echoes across the vast cosmic expanse. Where is everybody? For decades, this query has been a haunting undercurrent in our search for alien intelligence, crystallizing into what is famously known as the Fermi paradox. This paradox, first posed by the brilliant Italian physicist Enrico Fermi during a casual lunch conversation in the summer of 1950, highlights a stark, almost unnerving contradiction. On one hand, the sheer scale of the universe, with its estimated 200 billion galaxies each containing billions of stars, strongly suggests that life, and even intelligent life, should be abundant. Consider for a moment that our own Milky Way galaxy alone is home to perhaps 400 billion stars, and recent estimates suggest that at least 1 in 5 of those stars could host an Earth-sized planet in its habitable zone. With so many potential cradles for life, it seems statistically improbable that humanity is unique, or even among the first to emerge. Yet, despite decades of searching with radio telescopes, despite the tantalizing hints of exoplanets and organic molecules, the night sky remains stubbornly silent. There are no alien megastructures, no interstellar probes, no clear radio signals reaching us from the depths of space. For too long, the Fermi paradox has been framed primarily as a mystery of astronomy or biology. Is life rarer than we think, or do intelligent civilizations simply destroy themselves? But what if we approach this profound silence not as an absence of evidence, but as data in itself? What if the answers lie not in the biological rarity of life, but in the fundamental principles of information theory and the thermodynamics of civilizations? Instead of merely asking, "Where are they, Gabe?" we must ask a more challenging question. What does the silence itself tell us about the ultimate trajectory of intelligent information processing systems in the cosmos? One of the most compelling frameworks for understanding this cosmic quietude comes from the concept of the Great Filter, extensively analyzed by American economist Robin Hanson. Traditionally, this filter is imagined as a single, cataclysmic event, a hurdle so immense that very few, if any, civilizations ever pass it. Perhaps it is the difficulty of abiogenesis, the spontaneous emergence of life from non-living matter, or the inevitable self-destruction through technological hubris. However, when viewed through the lens of information theory, the Great Filter transforms from a singular event into a potential informational bottleneck. This reinterpretation suggests that civilizations might inevitably reach a point where the sheer complexity of their information systems becomes an insurmountable challenge, leading to a collapse not of their physical structures, but of their coherent organization and data management. Consider the exponential growth of information in our own society, doubling roughly every 2 years in the digital realm alone. As a civilization advances, its accumulated knowledge, its communication networks, and its computational demands grow to astronomical proportions. Perhaps a critical threshold exists where the maintenance, processing, and coherence of such vast informational architectures become thermodynamically unsustainable or computationally intractable. This could manifest as a system-wide crash, a loss of institutional memory, or a descent into a state so chaotic that interstellar communication or expansion becomes impossible. Alternatively, the informational bottleneck might not be a collapse, but a transition into a state utterly unrecognizable to us. A civilization might shed its physical form entirely, uploading its collective consciousness into a purely digital existence within hyper-efficient computational substrates, becoming a mind without a body that has no need, or even ability, to communicate across the vast emptiness of space in ways we can detect. Pushing this informational perspective even further, a radical and deeply thought-provoking solution to the Fermi paradox emerged in 2017, the estivation hypothesis. Proposed by a team of researchers including Anders Sandberg, Stuart Armstrong, and Milan Aturkovic from the Future of Humanity Institute at Oxford University, this idea suggests that hyper-advanced civilizations are not absent from the cosmos. They are merely dormant. They are deliberately sleeping, waiting for a far colder, more energy-efficient era of the universe. To grasp this concept, consider the staggering energy costs associated with computation. Every operation, every bit of information processed, generates heat, and that heat must be dissipated. In our current universe, billions of years after the Big Bang, the cosmic microwave background radiation, the leftover heat from the universe's fiery birth, still bathes all of space at a temperature of approximately 2.7 degrees above absolute zero. While seemingly cold, this background heat limits the fundamental efficiency of computation. Sandberg and his colleagues argue that from a purely computational perspective, it is vastly more efficient to process vast amounts of information in a universe that is far, far colder. Picture a future tens of trillions of years from now, when the universe has expanded and cooled to a mere fraction of a degree above absolute zero, and the stars have long since burned out. In such a frigid environment, the energy cost of computation could be billions of times lower than it is today. Therefore, the most intelligent and technologically advanced beings, driven by an imperative to maximize their computational potential and minimize their energy footprint, might be choosing to estivate. They could be in a state of deep, collective slumber, their consciousnesses compressed into ultra-efficient forms, waiting for the optimal cosmic conditions for their grand computational projects. Our current warm, star-filled era, brimming with the raw materials of hydrogen and helium, might be seen by such civilizations as a chaotic, energetically inefficient period, a temporary inconvenience to be slept through, much like a bear hibernates through winter. In this light, the Great Silence is not an absence of evidence, not a sign of our cosmic loneliness, but is itself the primary piece of data we have about the ultimate trajectory of intelligent information processing systems in the cosmos. It suggests that the future of galactic intelligence might be one of profound, calculated patience, and a waiting of the long, cold night. After charting the fundamental code of reality, tracing the biological urge for knowledge, and confronting the vast silence that surrounds us across the light years, a singular, breathtaking question remains. What is our true purpose in this immense cosmic drama? We have spent eons studying the universe as a grand, indifferent stage, observing its celestial ballet from a safe distance. But what if this perspective is profoundly incomplete? What if humanity is not merely a passive spectator, but an active, integral participant in an ongoing, evolving process, an essential voice in a conversation the universe is having with itself? Consider the speculative yet poetically powerful idea of cosmological natural selection, proposed by the American physicist Lee Smolin in 1992. This concept, far from being a proven theory, serves as a profound metaphor, inviting us to view the universe not as a static entity, but as something that might learn and change over unimaginable spans of cosmic time. Smolin suggested that universes might reproduce, creating new baby universes inside black holes, and that those universes which are more efficient at forming black holes, perhaps those with certain physical laws, would effectively parent more offspring universes. In this grand, cyclical vision, the cosmos itself could be evolving, favoring conditions that lead to its own propagation and, perhaps, its own increasing complexity. It is a universe that doesn't just exist, but adapts, refining its very nature through a process akin to biological evolution, a process so slow and vast it dwarfs human comprehension. The true philosophy of the cosmos, then, is not about relentlessly seeking a single, definitive answer to the universe's greatest questions. It is not about discovering a grand, unifying theory that concludes our quest for understanding with a final, declarative statement. Instead, it is about recognizing something far more profound, that we, the conscious beings peering out into the void, are the universe's current, and perhaps temporary, mechanism for self-reflection. Our very minds, our instruments, our capacity for wonder, are the universe's eyes and ears, its means of understanding itself. Think back to the earliest moments of existence. The fundamental laws of physics, those elegant blueprints of reality, gave rise to the intricate chemistry that forged the elements, the stars, and the planets. From that chemistry, across billions of years, emerged biology, the relentless, self-organizing drive of life, battling entropy and building ever more complex internal models of its environment. And from that biology, from the very cells seeking to minimize surprise and predict their surroundings, arose minds. Minds capable of not only surviving within this cosmic framework, but also capable of turning back, capable of comprehending the very laws that created them. It is a chain of emergence, an unbroken lineage from the quantum foam to the conscious thought. Our scientific inquiries, those meticulous experiments and vast observational projects aimed at mapping distant galaxies or dissecting the subatomic realm, are not separate from the universe. Our philosophical debates, those endless conversations about meaning, existence, and our place within the grand scheme, are not external to it. Even our artistic creations, from a soaring symphony to a single brushstroke on a canvas, are not detached acts of human ingenuity. They are all, every single one of them, a continuation of the universe's unfolding complexity, a testament to its inherent drive towards self-awareness. It is as if the universe, having laid down its fundamental rules, then spent eons building the very organs it needed to ponder its own existence. This journey through the cosmic script, the unreliable narratives of our ancestors, the ghost in the quantum machine, the universe's own boundaries of knowledge, the biological imperative for understanding, and the biases of our minds, culminates not in a final answer, but in a transformative perspective. We are not just living in the universe. We are, in a very real and fundamental sense, the means by which the universe is having a conversation with itself. The ultimate meaning, the profound purpose, is not to be found in some predetermined answer waiting to be uncovered, but in the very act of asking the question, in the relentless pursuit of understanding, and in the unique verse that each conscious mind contributes to the ongoing, ever-unfolding cosmic story. We are the universe's whisper, its query, its song, echoing back into the infinite.